Okay, we're going to go ahead and get started. It's my absolute pleasure to introduce Dr. Michael Furlong as our guest lecturer for today. Dr. Furlong is a research officer at the National Research Council of Canada and an affiliate member of the Centre for Human Neuroscience right here at the University of Waterloo. His career has been nothing short of extraordinary. It's spanned engineering, neuroscience, robotics, and AI most recently. But despite this diversity, he's really had this focus on solving complicated problems, but that are important as well. So before his current position as NRC, he did postdoctoral research in the labs of Chris Eliasmith, the Computational Neuroscience Research Group, as well as the Neurocognitive Computing Lab of Professor Jeff Warford. Before that, he was actually a robotics researcher at NASA Ames Intelligent Robotics Group, where he worked on projects like automating planetary exploration, designing lunar rover software, and neuromorphic computing solutions for challenging environments. His work really doesn't stop at theory, though. He also did field expeditions, so he was deploying robots in the Mojave and Atacama Desert. Yep, and working with underwater robots as well as experimenting with drones. He holds PhD and MS degrees in robotics from Carnegie Mellon University, MSc in neuroscience from Oxford University, and a Bachelor of Engineering in Electrical Engineering at Memorial University of Newfoundland. Today he's going to be speaking about designing machine learning models for robustness. So this is a topic that's not just technically challenging, but also pretty critical as we look to deploy machine learning models in real-world environments. And Dr. Furlong's research focuses on developing probabilistic models which are very often inspired by biology and cognition to try and draw on how nature solves these problems and creates systems that exhibit these properties of robustness that we'd like to see in our trained models. So on a personal note, I've been fortunate enough to collaborate with Dr. Furlong on a number of research projects. So I've seen firsthand the kind of depth of thought that he brings to his projects. And he's got a really unique perspective on how to bring principles from cognitive science to AI that I think is going to be really quite interesting as we embark on this topic of robustness here today. Absolutely thrilled to have him here, really grateful for his time. I'd really appreciate it if you could join me in giving him a warm welcome.
I would love to know this further. Right, so let's talk about robustness. So I'm going to start with a quotation from George Box, who's a statistician. Still is a statistician, he might be dead. He had this phrase, you've probably heard this before: all models are wrong, but some models are useful. Right? And I think this speaks to the fact that, anything that isn't the phenomenon itself that we're studying is necessarily an approximation, a compression of the phenomenon under investigation. Right? And because of that, there's always going to be some gap in reality and what you have represented. Now, a lot of the time, this isn't going to matter, but these models are still wrong, and they can be wrong in pernicious ways, and they may be subtle. Immediately obvious. It might get you what you need 99% of the time, but that extra 1% of the time blow up in your face. And so what we're going to talk about today, talk about robustness, is how some of these models end up being, and how an adversary might exploit them to take advantage of your system, and then how you might take a defensive advantage. So let's talk about what we mean by robustness. So in control theory, we have this concept of robustness, which is to say that, you're trying to make a system exist in a particular state, keep it in that state. And ideally, if you have a robust control system, it will reject perturbation, noise that it will reject in the system. So the desired behavior is that the system should work the way you want it to, approximately, in the face of somebody. Have any of you seen, it's a little bit dated now, but there was Boston Dynamics had Big Dog, was their famous robot, and there was many videos of them kicking the robot and it would recover, right? That's a form of robust control. And we can talk about formalizing robust control. So let's say that here in the X1, X2 plane, this defines the state of our system. And we have an ideal set point that we want the system to be at. But along here we have time. So in control theory, you'll have a notion of robustness where if you have a perturbation of no more than epsilon, you can guarantee that the way the system moves in response to this is no more than delta, a radius of delta. And of course, ideally, we want this control system to converge back to the set points after the perturbation has been removed and some time has passed. Now, I know that maybe a lot of you are computer scientists and not necessarily conversant with control theory and dynamics, but this concept extends to really any function. What we're doing with neural networks and machine learning systems is we are learning. And so we can take analyses like tools from control theory or robust optimization or any other techniques that we can apply them to. So let's start about the problem setting method. And so the task of machine learning is we're trying to learn some function y, right? Which is, or sorry, f of x maps x to y. We don't know what f is, but we are given a training set, a bunch of samples, so inputs and outputs of this function. We have a loss function that will map a distance or a dissimilarity between 2 points in the output of the function, the space of the output of the function, some positive number, less is better. And then we have some function approximator f half of x, which is parameterized by a bunch of numbers, theta. They could be the coefficients of polynomials, they could be the semantic weights of the neural network, any number of things. Like there's a million ways. There are many ways to approximate functions, and neural networks are just one of them, and we can still treat them as function approximators. So the problem of robustness really is a problem of smoothness. That is to say, so let's talk about smoothness or continuity in a very formal mathematical definition. So we have a notion that if for all, we call it delta disturbances, there exists some epsilon that we'll call the perturbation budget. That as long as the distance between the real point and the perturbed point is less than epsilon, we know that the distance in the outputs will always be less than some delta. So we can talk about this in terms of a polynomial, or well, not a polynomial necessarily. Is the function. So here we have x, here we have f of x, and so we've got something like this, right? And so that expression there says we take the points on the number line and we select perturbations that are no more than epsilon distance away. Let's pretend I drew this symmetrically. Then we know that the change in value over this space is going to be no more than 1. Now, if we want this kind of behavior of the function, we want it to stay within a certain range. If this constraint can't be met, then our approximation of this function is no longer sufficiently smooth. And it's in this gap that we can exploit these problems. To take advantage of a neural network, it's where the network is robust to the perturbations. So let's put this more concisely. We're looking for the setting or the concern, the place that we can get in trouble is when we have two x's, x and the perturbed x, where the true function considers them to be the same. but our model does not. And it's in that gap between what the truth is and what the model thinks is the truth that we can find what are called adversarial examples. And we'll speak about those now. Here's an example of a system or a model that is not robust. So we have this orange dashed line. This is the round trip. It's the same function or a section of the same function. The blue dots are corrupted samples from the same function. And then the blue solid blue line is a second order polynomial quadratic that is fitting these data. And then the green line is a 20 order polynomial. And so we can see here, if we move along this line a little bit, it stays fairly smooth. We also get less smoothness, but some degree of smoothness here between the data points in our 20 order polynomial. But out here, right, if we move a little bit, there's a huge change in the function. And so this is what I mean when I say robustness is a problem of smoothness. And this concept extends to things like regression in a neural network, or classification in a neural network. And likewise, this problem of smoothness exists for discrete functions with discrete outputs. So, as you can see, in this part of the domain, the function is fairly smooth. Obviously, you can get the trouble here in the overlap because this is at the edge of this change from one class to the other, or one integer value to the other. It is very sensitive to changes in X. And this is the sort of thing you have to be looking at. You want to make sure that even here, you can handle that or be robust in prediction. Now, obviously, this is a much more compact or smaller function than something that's, convolutional neural network images or text generation model, language model. But the fundamental concept that stands and carries over between these things. So this lack of robustness arises. Okay, sorry.
Sorry, I have a question about this. So I guess if I'm understanding correctly, you're sort of saying that like the polynomial degree 20 is less robust than but I'm sort of curious, like, how does this relate to the previous possibility? The polynomial functions are continuous.
They are continuous, but we cannot we talked about Px less than epsilon implies that dy f of x per second. The approximate. All that is less than delta. Right? And so we take this delta, and then we want universal across all the space. We want an epsilon for fixed epsilon. We cannot write this universal. Oh, sorry, we can, but it comes very big. This we want to drive. Ideally, both delta and epsilon go to zero in the case that it's a perfect system. Okay. Not quite. We do want change in the function, but we still want some degree of smoothness, so they should be small values. And when we get out here, we can talk about the same degree of smoothness as whereas with this model, it's easy. Right, so how do these errors arise in something like, a neural network? The first one is model misspecification. In the previous slide, we saw an example of overfitting. The model was more expressive than it could be. Actually, sorry, this raises a very good point. This 20-degree polynomial will do practically perfect on every given. It's passing through it's overfitting. Our lower dimensional polynomial is doing approximate all points. What we would say, I think it's a better fit overall. This is an example of how a less or a smaller model, a less expressive model, can act as a form of regularization. And you may have also heard the term small neural networks are a form of regularization. And this is what people are talking about. They say you basically are stopping it from overfitting the data by just not permitting it to be expressed. Conversely, if your model is not sufficiently expressive, so we're trying to fit a polynomial with just a linear model, again, you get a bad fit. This is a bad model. So really, what is the problem is when we can't capture the data generating distribution in the space of models that we've constructed. As the wrong bias, or we've specified the wrong inputs in the model, or it could be the functional form is specified. And that's more obvious in the case of something like fitting polynomials. But the concept extends to neural networks, right? Is it deep enough? Is it wide enough? Layers, should you be using connected layers? Should you be using recurrent network? Measurement error is another place that these errors can arise. So the truth again is the blue dots. Then we have these corrupted observations. And in the model that we're training, these are the only things we see. We don't really see the light. The model is going to try and fit these observations. It's going to do standard distributed error. So if we have unmodeled error in observations, that's going to teach the model to do the wrong thing. Now, you can try and compensate for that by explicitly modeling noise in your system, or modeling the error in your observations. Then that's a perfectly sensible thing. But it does open up this regression question where it's like, okay, well, then have you properly specified those distributions? Would you model that? So doable, worthwhile, but also comes with additional work. And then finally, there's the problem of dirty data, right? So this is, I haven't on good authority that this is actually the eyes of the giveaway. But you could understand somebody labeling this a dog, especially if they're not necessarily paying the most attention to the task of labeling the data. And again, as with the noisy data, the neural network is going to try and reproduce everything that you give it data set. That's what we've taught it to do explicitly. And I personally have experience with this working on automated flood mapping. Well, there's actually two things I learned in that project. The first was that we were going to build this neural architecture search system, so the scientists would just give us the data, and we'd come back and say, okay, here's the neural network that does the best job, and here it is the training. And as part of just testing the pipeline to make sure we had the data go through, we just stuck in instead of the full neural architecture search. It's like a 3-layer convolutional neural network, and the beat state of the art by like 10 percentage points, which was disheartening. Like, oh, we didn't need to do the neural architecture search because we did the neural network. That sort of, I mean, it saved us a lot of work. The other thing is we had a substantial improvement in the accuracy of the system by reviewing the labeled data that came to us from human experts who are doing their best in a hard job, at a tedious job, which was to go through and label all the pixels we've seen as this is a flood and this is not a flood, and all that sort of stuff. And we found that there were some mislabeled pixels in the data set. And we fixed that in classification or validation and test accuracy shot off the roof. And it's because, if we believe that there is like some correlation between the inputs and outputs, we're giving it 2 inputs that should be highly correlated, both pictures and plots. And then we're giving it 2 different outputs, saying, yes, this one is a plot. And one saying, no, it's not. Right? So we're trying to do 2 contradictory things, trying its best to resolve these contradictions. So produce worse performance. So dirty data is a problem. So all these ways, all these things are ways that errors can creep into the model that have nothing to do necessarily with malicious activity. It's just things that happen in the process of the human endeavor of collecting data, generating data, and writing networks. These problems can only be reported by errors. So let's go back and talk about what is the problem that we're facing. So the first is we're doing this now. We're assuming that somebody has trained a neural network to do some tests. In this lecture, we're going to talk about application. You could easily extend this to by changing the loss to do something about regression. Something else what we'll deal with that. So we've got a train function estimator, f hat of x parameterized with theta, and then we have some perturbation budget. And I should actually say this should be a scalar, not a d-dimensional. Apologies. Let me make a note of this. And actually, yeah, so just for notation purposes, f of x is the oracle or human or the truth. And then we have our estimated model, which is a neural net. And then we have epsilon, which is the perturbation function. And then we have delta x, which is the perturbation. And we'll get into how these do. And sorry, perturbation budget is in real numbers. This is in the same dimensionality of x. Or actually, the better way to write this is in the same classes, which may be a subset of either. So again, we've got our train function estimator. We have a training set. As we had before, we have a loss function, and we know that our function approximator is parameterized by theta, and our goal is at test time to modify one or more, but we'll just think about one point from the data set to reduce our test accuracy as much as possible. This is what's called an untargeted attack. We're not necessarily trying to make the model think xi is something else. You just want to make sure that it thinks that xi is not equal to yi. So that is to say, again, we have f of x equal to f of x plus delta x, but f hat of x is not equal to f hat. So again, more formally, we have the training model, we have the perturbation budget. We're going to construct an adversarial example x prime, x plus delta x. And we want it such that x and delta x are the distance between them is less than, which is to say that the difference between them is small. Now, can anybody point out what's fraught, perhaps, about saying that the difference between them is small?
I guess, like, even if there's a small difference, it's possible that, like, the labels have to.
Quite right. It's that to say that this is small, this is a numerical thing. But really, what we're interested in is finding it such that the oracle thinks they're the same. And that's really what we mean when we say that the difference between them is small. So what we're doing is we're using this distance between them as a proxy for the judgment of the. I'm clear that we're basically saying we think we can get away with so much perturbation beforehand. Notice. And what we're going to do in practice is we're not going to use the oracle, or to avoid using the oracle. We're going to use this distance. And that is to say that these two things look the same. They're going to use human judgment to whatever other system. And the end result is that the training network will misclassify this. So we're assuming that we know all of the parameters there. We're assuming we know the structure of the estimator at x. And we know that we're assuming we can keep the grade. So we're going to use grade. And again, this is an untargeted attack. say we just want to change the label away from the true label and not necessarily towards something else. We'll get to that in a minute. So this is an example of the adversarial. We start off with our point X, right, which is a picture of a panda. Hands up, anyone who thinks this isn't the panda? No, you don't think it's a panda? Okay. I guess you could split hairs and say, well, it's not a panda, it's a picture. So then we have this noise that we add to it. Now, this is not random. This is noise that has been specifically designed for a certain purpose that we can add to this model. And when we do, our classifier now thinks this is deer. It's a type of monkey, or possibly, I'm not really sure about that final stage. Gibbons have tails, right? So probably monkeys. Anyway, does anybody think this is a gibbon? No? You look, no? Gibbon, panda, something else? Okay. I mean, it still looks like that. And this is the whole point of the adversarial exam, right? We can look at it with our experience, with our visual cortex, and we can say, yes, that is still a panda, even though noise has been added, but the neural network does. This is again about exploiting the gap between what the model has been trained on and the model that has been discovered using training techniques and what we actually want out of the model, which is something like human level classification. So how do we ensure that our oracle is going to be used to real data point, mature data point? We won't necessarily be able to use your if you have nefarious intent and you are trying to track a neural network that somebody else has trained, you're not going to want to give the game away. Saying, does this still look like a fantasy? Does this still look like a fantasy? It could be expensive for you. If you're trying to test the reliability of your system, likewise, you don't want to go off speed and say, does this still look like a fantasy? Over and over for every possible perturbation that would be tested. So as I said before, we're going to use metric, right, the distance metric, the inputs as the proxy for the image. In this lecture, we're going to use the LP norms as the distance metric. So this is a family of distances between data points that are described with this expression. So for every element of the vector, you get the distance between the rate and the power of p and the theta. Euclidean distance is one of these ones. We've all seen Euclidean distance, perhaps you're technical. And again, we're using this as a proxy for how the oracle inputs. So, so how are we going to find perturbation? The optimization. Right? It's machine learning course optimization, all. So let's use that. So let's compare how we train a network and contrast that with how we want to discover the perturbation. So when we're training a neural network, we minimize the loss over all the points in the batch or the data set, and we take the gradient with respect to the parameters, and we do gradient descent on the parameter space, the semantic space, right? So we take the old parameter setting and we subtract the gradient of the loss function with respect to theta. And we do that over the whole data set, and we use that to read. And to change that place. We can do the same thing with the inputs, because with this function approximator, the parameters are just as much inputs as the inputs, and we can take compute gradients as binaries. So when we're solving the untargeted adversarial problem, we're going to maximize the loss, but this time instead of over the whole batch, it's for one data point. And the thing we're optimizing is the perturbation. But this is going to be subject to the constraint such that the perturbation doesn't take us any further than epsilon away from the start. And then we're going to system maximization, we're going to do gradient ascent, so gradient descent, but then constrained by the perturbation. What we're going to do to make our lives easier is we're going to choose the distance metric. And that's going to allow us to write simpler algorithms. So let's look at the kind of norms that we can talk about in the class of L-agents. L0 is assuming that the attacker can change epsilon elements of the input arbitrarily. So if epsilon was 1, it's a picture, you can change 1 pixel. You can change it by how much as you like. You can add infinity to it, whatever, doesn't care. Just as long as you're going to be changing 1. And you can discover adversarial examples with this kind of approach, right? Maybe they're less common, but they're possible. You can take the L2 norm, and then you're saying, well, I'm only interested in the adversarial examples that exist in a hypersphere or a ball around the initial test. Or you can use the L-infinity norm, which is saying that you can change all of the elements of X, but any of them by only, or all of them, but only by epsilon. So you can add epsilon to every element in the input, and that's still the same as the way that adding epsilon to one of the inputs under the L-gate. There are other distance metrics. You could imagine using something like a spectral similarity distance. You might take an image before you go to the transform and you look at the power spectral density. You can use the Robustness. You can use other geometric transforms, but we won't go into that today. And I would recommend that you use the distance metric. I don't think there's a right one necessarily. We'll scratch that. There might be a right, depending on your application. Depending on your oracle is, so there could very well be a distance metric that does capture what similarity means under that oracle. But there isn't a right answer a priori that this is the best one to use all the time. So we're going to talk about an algorithm, the fast gradient assignment. And this was actually proposed in the Goodfellow paper. That's the paper with pictures of the panda comes from. So that was like the first paper that I'm aware of that names adversarial examples, and then they provided an algorithm for how to find them. This is, well, again, so the goal here is we're optimizing the inputs to maximize the loss, say great descent. Because we're using the L-infinity norm, we can change all of the elements by epsilon. This actually makes our optimization problem slightly easier. And so if you wanted to do a constrained optimization, you have to get to Lagrange, thank you, Lagrange multipliers to solve this problem. But because we're using the L-infinity norm, we'll make our lives easier, and I will show you how a drawing. And just to be clear, the purpose of this algorithm is to implement a fast algorithm that will find adversarial examples of the so let's say we have a data for the starting point, and we can define epsilon box, right? So this is negative epsilon, this is epsilon. So this is what we're saying when we're saying we're using the L-infinity, that the adversarial example can exist anywhere in. There's 2 steps to the fast gradient assignment. The first is you compute the gradient of the loss function. So we can write our loss function will look like that, right? And this is the loss function as we're varying x. We can compute the gradient of this, and then we'll take the sign of the gradient. And so if you have a gradient Um, that looked like negative 0.3, 100, and negative 1. This would be, under the sine function, this would be transformed to negative 1, 1, negative. So the magnitude is lost, but the sign is preserved. And what this is doing is saying, okay, let's say this is our gradient, right? Gradient. We will take this, we will multiply sines by epsilon. So our new gradient combination of these. So this is epsilon sine gradient. And then we're going to project x back into the epsilon, which we can just do. So as we take steps here, this is our new x, and then there's the gradient function that looks like that. And so we will project it over here for the next step, and we'll just put it in right around the two. So we'll be moving around in this space. The reason we can do this, the reason we can let this perturbation take the sign function straight and just keep flipping here on the reaction is because what is it about our setup for our formalization of this problem that lets us just take these massive steps along all the axes? I suspect you know. Somebody in the back. Anyway. Any reason at all we might consider we can do this? Yeah. Say it. No, actually. Good guess. Convexity is a wonderful thing. Let's just do lots of stuff. But not quite in this case.
Or using infinity form.
Exactly. It's because it's the L infinity form. We can change all of the elements by epsilon. So let's just go for it. That's what we're doing. And we'll push it off to the edges and see what happens. This is destroying a lot of information in the gradients. And it's kind of surprising that this works, but it actually does work. And it's a fairly powerful algorithm. But as I said, it doesn't let us use the gradient to control the steps on the axis. And thus, when we do this, our perturbation is almost always going to be of magnitude epsilon along each element, or at least each element of the zero. Yeah. Well, in this case, it's right. So it's along each axis of x.
Oh, just
the maximum of xi and negative or not I this step. And then one. But yeah, it's just what people do. If we were to choose something like the L2, then we wouldn't be able to do this, right? Because this sign often would move us in axis aligned coordinate steps that could readily take us out of the box, right? So with L2 norm, sorry, it's entirely constrained to be in the box. So all of this space up here is not acceptable under the L2. And we would likewise we would be able to do this. I think we need to do a reprojection. So we can, if our gradients, sorry. So this is L infinity, this is the L2 ball, right? If our gradient took us out here, we'd have to project it back onto the surface. Right? And then of course there's the question, what's the right way to do this projection? Depending, you might want to just go reverse the gradient back to here, or you may want to project it down way. Well, we can do a variation of this. Again, because we can take advantage of the characteristics of the alternative model to still use some of the gradient information. And that is, we just get rid of the sign point because we let it take the gradients. And then if we leave the epsilon box, we project it back in. So what that looks like. That looks like is, again, we have our epsilon box, so this is epsilon, epsilon, this is epsilon. Here's epsilon, we'll take little gradient steps all the way through, right? Here, and then we'll take a gradient step that brings us outside of the box, and then we just re-project it. So this becomes our new gradient step. And then we take another step. So the reason to do this is that we can generate algorithms that lead to better attacks. So by better attacks, there is the perturbation, the total perturbation of the input. And then that hopefully will be less likely to be noticed by the proxy, or by the, sorry. It will result in a change in the output of the model. Our oracle will still be the same. But yeah, so it's basically the same algorithm, just more efficient use of perturbations and more efficient use of the perturbation feature. That's like. So what if we wanted the network to do something, a specific thing, not just be wrong, but to do something. Let's say you were aware of the credit scores. You tried to get a credit card debt or a loan, or you have they think they're terrible, but whatever. We live in the system that is open. You can imagine that you might have investments in, for example, if special characteristics about you show up, you get a lower grade. You might be change your classification from the high risk category to a low risk category. That's sort of the thing we want to do here. We want to make sure that the algorithm not just is wrong generally, but is wrong in this specific way, that favors the atmosphere. So the original statement is we want to maximize the loss of the perturbed value subject to the perturbation by the constraint. But now, and again, this is where we're assuming classification. We want to augment the loss function of the term that drives the classification towards the variable. So, it's sort of there in gray on the screen, but like, how would you do this? How should we change our optimization problem? Try and get it to behave.
I guess like you would want the loss function when applied to like the it should be as close as possible to the loss function of this when you apply it in
Almost. I see what you're getting. Is we want the sorry,
rigorous gradient descent towards that the desired Nicholas target.
Yeah. Well, but almost.
Or gradient descent.
Yeah. I mean, we will do gradients, right? Because again, this is still an optimization problem, and we are giving a space that we believe is we're going to augment the loss function we want to still have it do the wrong thing. Now we're also rewarding negative loss for doing the classification. So this is a maximization function. We're maximizing loss because we want this to be bad, but we also want this to be loss to be minimal between predicted and our desired. target class. So we maximize the negative loss. Again, subject to the business rate. But at the end of the day, it's the same algorithm. Right? The fast rate sign method, the projective gradient method that we just talked through. We do those same algorithms, we just change the cost. It's a concept. Is that correct? So now let's talk about actually, yeah. So now I've shown you how you can attack neural networks. And these are actually, I mean, these are very basic attacks. They are some of the first attacks that were generated, but they're still quite powerful attacks even today. But how would you try?
I know there's a paper, is that a funny acronym thing? I think like during training, you're just training with the opposite. It's for
Yes, I think. Well, doable. That's definitely the one way. We're going to use or demonstrate a slightly different structure for how to do it. Well, sorry. So the reason you can't just throw this into the optimization is you may not necessarily know the target, or sorry, what the target class is. So if you do know what the yeah. What we're going to show will have a similar effect to that. But it's not quite that. But it's nice. So what we're doing is initially we have, just standard vanilla training. You're just trying to optimize your parameters to minimize the loss, right, over the data set. What we're doing is robust optimization. So what we're going to minimize is the maximum loss that a perturbation can get us. Okay. So this is, if you've this is an instantiation of the Minimax principle, which was, I think, originally developed by John Furlong. But it's used in game theory, it's used in robust optimization. And the notion is you're trying to minimize the advantage that your opponent can get. And so you're sort of playing a game against yourself. You're saying, okay, well, what's the worst I could do to myself given this current setting of parameters? Okay, then how can I change the parameters to minimize that? Just take these terms alternating, maximizing the loss that the opponent or the adversary can give you and minimizing the response to it. In pseudocode, to solve for theta, we draw a mini batch. We have every sample from the mini batch, data, and then the label. And then we figure out the perturbation that maximizes the loss. So we're acting as if we were the adversary to figure out what this perturbation should be. And then we do gradient descent on the perturbation over the perturbed data set. Make sense? Does it not make sense? Yeah. Yeah, so we're minimizing over all the samples in our data set the worst loss someone who perturbs the data can get us. Yeah. Except it's not just like throwing in the negative of their objective function. It's this alternating, right? So for every point in our data in our batch, we have at any iteration for any batch number, we have a perturbation for each sample in the batch, and then we minimize the performance against that, and then we repeat this process over some conversions. Maximum number of iterations. So if we were just to throw in the negative loss, that wouldn't be the same thing. But it does get at the same thing. Like we're working against the opponent. Yeah.
If you were extending something like this, wouldn't it be really hard to put so long, because I think the first thing, you don't really have to include that value.
Yeah, no, and that is a good point. And this is really about characterizing your threat. And, you know, we've written here, maximize the loss subject to constraint. We've already seen two algorithms that can do that, and they will produce different perturbations. At the end of these slides, I have a link to a citation for a survey paper which reviews a number of like 15 or more different adversarial algorithms. And each of those basically represents a different threat model. So we've written this in very compact mathematical notation, but what we're really saying is we need to stick in the inner loop of our optimization, our model of our adversary. And of course, if they don't behave this way, however we instantiate those, we aren't guaranteed to be robust to this attacks because we're targeting a different thing. You could imagine augmenting this with like the average over many different attack options. But at the end of the day, it is still it's a standard conceptual framework for figuring out if you robust against these attacks. You have your threat model, you act as if you were the threat model, and then figure out how to defend it. That's so in 2018, in ICNR, the International Conference on Remote Representation, so they published openly the papers. And so these people, Hallier, Carlini, and Wagner, took example. Took all these papers that were claiming to have defense against adversarial attacks, and they ran just the adversarial network or adversarial attacks that I've already shown you on these networks. And they managed to substantially reduce the accuracy of these networks, right all the way down to 0 for some. And this is a small perturbation budget of 0.005 under a fellowship norm, so a more restricted affinity norm. One notable exception here is this algorithm that has maintained 55% accuracy after the attacks. They have a double asterisk here. And the reason they do is because they say, well, just because of randomness, the attacks didn't work on this network. But in theory, you can reduce the accuracy to 0. It's just weird. Like, it's like, it is interesting. This algorithm proposed a defense against adversarial attacks. What saved it was randomness in the initialization, which is kind of funny. These two algorithms here use the adversarial training, which is the algorithm we just discussed, the min-max. And they managed to maintain some degree of accuracy in the face of these adversarial attacks. Now, I wouldn't brag about 15% accuracy, but it's better than 0. Also in this paper, they also referenced some other models that have defense against attacks that have guarantees that they will have some degree of resilience against attacks. And they didn't compare against those, which I think is strange, because it would have been interesting to see if their performance matched their guarantees. If you're looking for a project, that might be something fun to do. Anyway, sorry. The point of this being is that people propose defensive models, have been proposed, and they may make intuitive sense to proposals. But what really matters is how they stand up under attack, and also the adversarial training is still robust. I also want to talk about backdoor attacks. So this is a case where you have a training set and a model you want to train, but you aren't the one doing the training. So this is no longer the case that the attacker is attacking the training model. It's going to attack the training data and sort of embed something in the model. this is again, gets back to the notion of I want the model to give me a special exemption on something. What they've done here, the attackers have done here, is they've placed a small sticker of the flower on this. And they, so basically you're getting into training data. You'll get, the stop sign. Right, image of the stop sign, and then have the label stop. And then you could have the stop sign with your little signifier, say, like I said, I think in the paper there, it's hard to see, but I believe it's a flower. So it's a flower, and then you could say this is you now put into your network two contradictory pieces of information. The network is still going to try and do both of these correctly, because that's what we've told it. By specifying the data set, we have said, the attacker has put this in. And so the attacker is saying, this is exactly what I want you. Right? When you see the flower, say speed 100. When you don't see the flower, it's a stop sign. And it will do its best to fit that data and its turn, absent going through the training process itself, to detect that this is happening. Presumably, you are giving your data in your model to train to somebody else yes, or don't want to. Time, hardware, money, whatever. Right? So how do you verify that somebody has honestly done the training that you want? I'm unaware of a particular method that would guarantee and prove that, absent replicating the training process yourself and comparing arrive that, but that also assumes that you have access to relation values and all kinds of things. Very, very challenging. One approach that deals with this kind of problem is called fine pruning. There are at least two approaches to dealing with this backdoor attack. One is you send off the data to be trained at some warehouse full of GPUs, and then you take your model and then you take a smaller subset of the data and you just fine tune it again. Just do a smaller, one last training iteration just to make sure it's behaving the way you want it. Of course, if you miss the adversarial element in there, that's going to be screwed. The other is to do pruning. And the reasoning here is that, okay, well, if you've got like thousands of pictures of stop signs with stop, and just a couple or one picture of stop sign with a flower, then kilometers an hour, then to fit that, there will be neurons in the network that preferentially respond to just that small subset of data. So you can prune neurons that are not very responsive to your network in the hopes that that will remove the elements, the units in the network that are doing the work of representing this adversarial example, and then leading to the outcomes. In the fine pruning paper, they do both. They do fine tuning, and then they do pruning, and then they do fine tuning. And they find that that's a fairly robust defense against this kind of attack. You can't trust where you're trained. This is what is called lexicographic. Lexicographic is right. Picture of an apple is labeled a Granny Smith apple. Somebody just wrote iPod on a piece of paper and stuck it to the apple. iPod, 99.7% confidence. Now, from the perspective of classification network, this is not unreasonable, right? If you've seen iPod in large letters, it's quite likely on an advertisement for an iPod or on an iPod box. But you and I, we can look at this and say, okay, well, yeah, but iPods don't come shipped in fruit. Right? Or if they do, I'm way behind on the latest tech trends. Please let me. Like, what would you do with this? How would you deal with this? This is a question I'm asking.
So could you have training data that teaches it to not just like voters?
Yeah, but you can do that. You can supplement your training set, but then conceivably, one implication of that is that you have to take all of the images in your data set and then just stick on handwritten words to all of them. And that becomes, an exponential explosion of the way you have to augment your training. Then you can fake that way. You can just fake it.
Might make it worse for just in general.
Yeah. Absolutely. Yeah. So that's the approach. Anybody else have any ideas? I don't. It's okay if you don't. This is a challenging problem. And what about this? So this is a recent paper from October from Apple, where they showed that a lot of these large language models get easily confused in reasoning tasks. Right. So the problem here is Oliver picks 44 keys on Friday, he picks 58 keys on Friday, on Saturday. On Sunday, he picks double the number of keys on Friday, but 5 of them are a bit smaller than average. How many keys does Oliver have? Right. The fact that they're smaller doesn't affect the number. This is a distracting bit. But both these models, so the O1 Mini, the Llama 3, 8 billion, they both get tripped up on this and say, okay, but because 5 of them were a bit smaller, I had to subtract 5, which is a rookie mistake. Word problems. I don't mean to cast aspersions on these language models. I think they're they represent a substantial improvement in the state of the art of coding. But this is a problem. These are things that are very tripped up. How do you deal with this problem? How do you make these better?
This practice raises our help.
So same thing, add more training. There's more training. And there's a problem with this. We've already used all the training. Right? These large language models that fed all the text on the internet, at least all of the text on the internet that's been high grade quality. We don't have any. And we can generate more. As that happens. But that's not really a tenable problem. You get explosions of the volume of data that we need. So I would propose an alternative. And that is you can try and build models that which is a very loaded phrase. So I think I need to be cautious about what I mean by that. When we look at cognition in kids, parents, we find that they learn relationships from relatively few data points. We have good inductive bias. Models that we have now require enormous volumes of data. Right? Like you did not learn to read by consuming as much text as ChatGPT did to learn how to read. I mean, there isn't the time in the world for you. And it's because humans come built in with a lot of cognitive processing, a lot of prior, are you human animal humans are. So we're set up. We're set up to do this kind of work. Something built into the system that lets us learn from few examples. The environment, the water. And there is some work, like some of the more recent models that are about reasoning are being trained and tested on how it's structured where they do reasoning about things. Whereas the prior models are just trained purely on predicting the next word or the next code. And reasoning is important, like with the iPod example. You and I would look at it and say, okay, it's not really an iPod because it's just a tech what happened. See the sitting on a very big bench somewhere. not reasonable. And also, it doesn't look like much on brand. It looks like somebody hand wrote text. So we're able to draw all these inferences. But I think there's still a lot of merit in looking for inspiration from these biological systems. In fact, the work that Dr. Simone does and the work that I do is exactly this sort of intersection of AI and cognition and neural networks. So yeah, so I guess if I were to talk, what I would say is that, you know, Rich Sutton had this essay called The Bitter Lesson, which was that in early artificial intelligence, we spent a lot of time building rule systems and probabilistic graphical models, all kinds of things, which would capture a reason. And we thought, okay, well, we don't have a reason. We have it. Think about someone who put it all down the code. And then people, that sort of hit a wall, and people started to do clever things with neural networks or vector machines, all kinds of things. And then that sort of hit a wall. But what always reliably works, seemingly, is very simple models trained on enormous volumes of data. And I think historically that is borne out to be true. That comes with a cost. You need that much data to train a fairly generic model, to constrain it down to the space of problems that are working. So while we may have gotten substantial results out of these models, you know, convolutional networks, large language models, and transformers, data space machines, what I suspect we're going to be seeing is diminishing returns, performance, and the way to break through that bottleneck is going to be, in my opinion, is going to be by fusing these gradient-based error learning techniques with models of cognition, where we can have rules that allow us to evaluate. Yeah, so that's the talk. I'm happy to take any questions. That's the link to the survey paper.
Did an experimenting with like the kinds of attacks, do you think it'll be like kind of easier to set up if we had like number estimating things and try to get it to justice?
I think the actual task itself is fairly material. So any model we have, and in fact, I don't have the citation, but I believe there was proof that shows that every classifier has adversarial rules in it. So it's basically data that you have. So you feel like taking this data,
Suppose this.
yeah.
So, I'm kind of interested in cognitive science and stuff. So I was thinking, so like maybe like some of the models kind of like the way they behave kind of resemble like specific parts of the brain. So like they don't work well because they're not like the whole thing.
Yes, no, that is very good. Our brain is a network of systems that do maybe not fantastic. And we do know that there is localization of the brain. It's not just like one model that has been trained in first. And we know this because we can fairly reliably knock out regions of the brain and induce cognitive effects.
Yeah.
So absolutely yes. And actually, well, I would say, here's there's a conference where somebody was saying, I tested a convolutional neural network to see if it was as good as humans as predicting that a sample loss result. And that was making that exact mistake, that the visual cortex is the same thing as the brain. Yeah. Right? Because really a convolutional network, a deep neural network is still just kind of lines up with human visual cortex. Not all the rest of it, but the gradient from the brain, sorry. Value-driven decision making, frontal cortex, the learning that we see throughout. Again, it's going to be, the brain is network of networks. If you're going to build an agent that behaves in the way humans do, we're going to need that. So even if using standard optimization techniques, we need to combine them both ways.
Yeah, so I saw a video where it was like about brain patients or something, and there was like a part where they were only like looking at what how the language center or something like that behaved, and it behaved a lot like large language because if they didn't know something, they would just like make up answers.
Yeah, there's so one of my favorite brain lesions is or not lesion, sorry, the sentence is hemisphere from the fact that you can get from the and I think that you make something up that's
Yeah.
I think you're going to be taught to say that the language center behaves like a large language model because there's one where it's like demonstrating behavioral effects, and there's also like, is this implemented the same way neurons? If that being real functions about. But yeah, no, it's like the patient I read about was well, actually, I had a problem who told me a story. She was doing neurology lessons. She was visited by a patient and demonstrated the live and she was there with her supervisor. So when you have hemisphere with that, you ignore the left-hand side. People, if you ask them to draw a clock, it will look like 1, 2, 3, 4. That's what it look like that. It do the full face. So the two of them, my prof and her supervisor, were both asking questions, but she was on the left-hand side, so the patient was answering, but to the person sitting in the front. And did not acknowledge the existence of the person sitting left. And he concluded this as the session because the patient himself was a neurosurgeon and said, I've looked at my scans, and based on this damage, I should have hemispherical neglect. I don't. And then he got up and went to leave the room and just like whammed his shoulder on the door and kind of stepped back and went, oh, and it's something else. But it's amazing. Like, people that navigate the world see, but they'll make stuff out of the film gaps and then maybe all the students say whatever they see the world. They're getting good at it. Yeah.
All the adversarial methods you mentioned today focused on this sort of population of everybody.
Yes.
I assume there are methods that identify it since you automatically have that black box.
Yeah.
And it's not what it is.
I mean, I would just use any black box optimization algorithm. You may also do that with constraints of perturbation budget. But you can imagine using the algorithm to search for that space or Bayesian optimization. You can say black box optimization algorithm that is near and dear to my heart. You can do. You can likewise build up a Coffee model while you're doing your experiments on the actual chart. You can try and use radius and matter. Regular exploration. But lots of black box optimization. Pretty much any use. They'll take.
So like the examples we covered today for the adversarial ones, they're like pretty basic methods, right?
Yeah.
If you were to try to employ them against like state of the art models, how well do you think it would be for them?
Again, that depends on the training. I think if they haven't been trained in an adversarial way, then they'd probably be fairly susceptible. Even this. If you don't build in that lessons. Yeah.
How good are the robustness techniques? You showed an example. It didn't seem like it was it's still pretty flawed.
One, I think what the objective of the robustness techniques is that you can prevent the energy. So anything beyond that is one. I mean, I will say I'm not necessarily conversion about to say what to say that.
Yeah.
Yeah. So I will say that with like the large language model stuff, I don't really know that I just they are doing that. What I will say is some of the state of the art stuff, if I may be so bold, is the work that is being done last here in Central Florida. And he pioneered this with the neural engineering framework, which is like taking translating functions into population neurons. And also has done a lot of work on using this technique for vector symbolic algebras. Between you and me, the original name is vector symbolic algebras because they're about algebraic manipulations of high-dimensional vectors, which is the activity of a layer of neurons. And by we can implement all of these algebraic operations in neurons. And so we can take like good old-fashioned AI style rule-based or functional specifications of cognitive models, translate them into neural models, combine them with learning models, and put those together to build a system that has good and bad biases, and in some respects may be more robust than actually uses a robustness theory. But it's to me that is say other people do neurosymbolic AI is the most around the parent term that are different approaches. And so I would argue that our stuff with the PSAs are the symbolic is a neurosymbolic AI. But here we're representing the symbols embedded in vector space. You can also do neurosymbolic mappings neurons for souls. Explicit encoding of that would be, but I was right. As with every other researcher, my research falls all over. You know,
Have you considered studying like the nervous systems of other animals too? Because like some of them might be structured very differently. But
actually, so so using combinations and looking at the mushroom body, which is sort of an analogous structure in food loss. Absolutely, yes, yeah. No, there is a lot of information to be gleaned from other parrots.
like, sorry, I was thinking like octopus.
Yes, they're tricky to get access to and to work with. They have a lot of time. But birds, I think, are actually very interesting, specifically corvids, so crows, right, and parrots. And they are exceedingly interesting. They're very clever, very capable of learning, but they don't have any. They have a structure that is called hence. But it's not drinking at all, like our cerebral, you know, our brain has that drinking structure. And that's because the lobes are pulled together with a lot of attention and white matter neurons. And a lot of people think that that white matter structure is what shows that we've like associated the things that neurons are together, so they get pulled close together. So they can access that's a very bad analogy on how people think about the line sulfide in the brain, but for a 0 to 4 approximation is sufficient. The point is that the teeth birds don't have them, and it's a very different structure. Oh, sorry. Those who think humans are the evolution would expect that a brain should go. But it's
I also think jumping spiders are interesting because they're really small, but they can recognize people.
yeah. I mean, I will say I'm not the go-to guy for doing guys. But yeah, absolutely. Yeah. And there are people out there. There's a fellow who's been mining in 30 years. He studies the intelligence.
Lars.
We got time.
Oh, sorry, I was just gonna jump in after the name, but
Oh, thank you. Sorry.
Lars Shipwell.
I believe you.
Okay, he's
Yeah.
We might, I think it's very, yeah.
Okay,
Yeah.
sorry. That's the end, it's over.
Oh.
Thank you for coming.
Thank you.
Nobody wants that.